Well, let's continue our discussion on acids and bases. Last time we defined an acid as something which has a low pH, lower than 7, and we defined a base as something that has a higher pH, greater than 7 up to 14. 1 would be a very strong acid, 14 would be a very strong base. And those numbers 1 through 14 are what we call the pH scale. P means potential, and it's all about hydrogen. So Arianis and Ronstadt and Lowry defined an acid as something which gives a hydrogen. So hydrogen means acid. So we would assume if something has a lot of H, it's very acidic, it would be a low pH, 1, 2, and 3. We would consider a base not to have a lot of hydrogen, so its pH would be very high, 10, 11, 12. Okay, let's take a look at the numbers a little bit. Now, how do you get those numbers 1 through 14? Well, it is a special mathematical function called a log. Some of you have seen this before if you're in Algebra 2. If not, that is the function right there, log. It's on your calculator. Here's how you do it. You take the hydrogen concentration, right? So let's suppose hydrogen goes in here. You plug it into your calculator, push the log button, converts into a logarithmic function, then you take the negative of it. So, if you'll follow along with me, if you got your calculators, let's go ahead and do some of these. Suppose we do this one here, 0.1. Put 0.1 into here, take the log of it, that should give you negative 1, and if you make it negative, then this comes out to be positive 1. So, if an acid has a concentration of 0.1 molar, it would have a pH of 1. How about this one? 1 times 10 to the negative 5, very, very small number, that's 0.000001. Put it into your calculator, that gives you negative 5, and if you take the negative of it, it gives you positive 5. You can see a little trend here. So if the exponent here was negative 5, you can see that we're going to end up with a pH which is positive 5. And I bet you can guess what this one would be. If you have a very, very low concentration of hydrogen, 1 times 10 to the negative 8, it would give you a pH of 8. So that'd be an acid, strong acid. That'd be a weak acid, pH 5. And that'd be a base, kind of a weak base. Okay. Now, besides doing pH, you can also do pOH. That is, what is the potential of the hydroxide? So if you wanted to talk about things just in terms of bases. Same calculation. It's the log of the hydroxide concentration. So if I was to say, for example, that I had sodium hydroxide, sorry about that, that doesn't look at all like sodium. I think I may actually need to type this out. So if I put in, shall we say a 0.001 molar sodium hydroxide, okay? What would be the hydroxide concentration here, right? Well, that's very simple, right? The hydroxide concentration would be the same as the base, 0.001. Very good. Okay? So you would put that number, right, into this equation. That would give me negative 2. And if you take the log of it, negative, it would give me a pOH, right? So now you get a pOH of 2. Okay? Now, we tend to talk to things only in terms of pH, though. So how do you go from pOH, what is the concentration of hydroxide, to the concentration of hydrogen? Very, very simple. They always add up to 14. So this is some pretty complicated math, right? If the pOH is 2, what would be the pH? Well, what number adds up to 14? pH must be 12. And if it's pH of 12, we know that this would be a basic solution. Okay, why 14, right? Why 14? Well, the reason is that when you look in water, the hydrogen concentration is 1 times 10 to the negative 7. And when you look in water, the hydroxide is exactly equal. That's why it's neutral, right? It's also 1 times 10 to the negative 7. So you would get a pH of 7 a POH of 7. If you add them together, 14. That's why everything is based on a scale of 1 through 14. Okay, take a moment. I want you to draw this figure down here. This is the figure we're going to use to go back and forth for all our calculations. Now we already saw, for example, pH to POH. How do we go back and forth? By subtracting 14. So if I had, for example, over here, right? If I had that, the pH was 3, subtract from 14, what is the POH? It would be 11. That's really easy. And if I had, let's do it the other way. Suppose I said the POH was, what number shall we do? How about 4? Then what number subtracts from 14? That would give me a pH of 10. So really easy to go back and forth using this scheme from pH to POH. Okay? Now how did we go from pH to hydrogen back and forth? It was the log. So if you had, over here, shall we say it was 0.001, take the log of it, negative log, and that would give me a pH of 3. Very simple. Now, same thing goes down here to go from OH to POH. But the more interesting question is, how do I go backwards? So, suppose I had, a pH of 5. What is the hydrogen concentration over here, right? Well, it's really easy. The opposite of a log function is 10 to the power. So, if the pH is 5, what is the hydrogen? It is 10 to the power of negative this number, negative 5. The hydrogen concentration at pH 5 is 10 to the power of negative 5. Hey, let's make it really complicated. What if I said that the pH was something weird? What if I said the pH was 4.3, right? What would be the hydrogen concentration? Follow this, right? Here you go, right? It would be 10 to the power of negative 4.3. That's the hydrogen concentration. And we could do the same thing here. If the POH was, 6, what would be the hydroxide concentration? 10 to the power of negative 6. Okay? Very simple. And then finally, how do we complete the square? Well, the last thing you have to do to complete the square, right, is go from hydroxide to hydrogen. And I said it's all based on water, and that's 1 times 10 to the negative 14. That's going to be our secret number. So no problem. Suppose I said the hydrogen concentration was 10 to the negative 6. How about that? 10 to the negative 6. What would this guy be? What two numbers get us to negative 14? 10 to the negative 6, and then this must be 10 to the negative 8. Like that. Very simple. So why don't you finish copying this down, and then we'll try and use it. Okay, let's go to the next screen. Alright? Now, in our experiment today, we're going to go ahead and go back and forth and measure the amount of moles to titrate something. So if you start with a base and you add acid to it, it'll exactly get to an equal point when the moles of acid is equal to the moles of base. Our equation for this guy was, right, remember, MV1 equals MV2, where this is an acid, yeah, and this other guy here would be the base. MV is the moles, right? So we're going to titrate two things today, both a vinegar and ammonia. Vinegar is an acid, so we titrate it with a base, and ammonia is base, so we titrate it with hydrochloric acid. Let's try it here. Let's do a very simple example of it. See if you can do this one using our equation, right? Suppose I have 0.2 molar solution of sodium hydroxide. All right? And how much of it would neutralize 100 mils of a 2 molar? let's set it up here. Moles times molarity times volume. Molarity times volume, right? So we got 100, yeah, times 2. Okay, that's the acid, yeah, equals the base. How much of the base would be titrated if it was 0.2 molar? Well, this is 200, yeah, and this is 0.2x. Divide by 0.2, and we get 200 divided by 0.2. It would take 1 liter. So 1 liter of the sodium hydroxide would titrate 100 mils of a 2 molar hydrochloric solution. You try one. See if you can do this one. Suppose I have 50 mils of a 0.4 hydrochloric solution, and it's titrated with 100 mils of sodium hydroxide. What must have been the molarity of that base? Let's set up the equation. MV1, right, equals MV2. Very good. So 50, let's go ahead and do that. So 50, right, times 0.4. That's my acid, 0.4, equals 100 mils of the base. I don't know what the concentration of the base is, right? Let's spread that out. So, 50 times 0.4, that is, what do we get for that? Is that 20? Sounds like 20. Equals 100 times the base. 20 divided by 100 is 0.2, so that must have been the molarity of the sodium hydroxide base. And that's how you can do a titration. If you use a known acid, you can figure out an unknown base, and vice versa.